In the previous section, we tried to solve the governing differential equations by obtaining the exact solution of these equations, and we realized that even for a very simple loading case, the solution is very complicated. Now, because of this reason, now we will look at the numerical solution. So we say numerical, which methods we can use to solve this equation of motion. So we will be first checking the finite difference method. Let's first look at the forward difference. So we have, let's say that that's t, we have a function f of t, and it has a variation something like that. So we are at this current time step, let's call it Tn, and at this time step the value is equal to f of Tn, and let's say that we go by delta t amount. And now we are at t n plus 1. So what we see here is, this is, and this one, f tn plus 1, and we are interested in the slope of between these 2 points. So we are just linearizing the variation between these 2 points, and that will be delta f tn. Okay, now the first derivative of this function, df tn divided by dt, the first derivative will be the slope of this line, which is equal to delta ftn divided by delta t. So I can just write it this way: f at tn plus 1 minus f at tn divided by delta t. So that's the first derivative. And now in the equation of motion we also need the second derivative, so let's figure that out. So dt squared is equal to f prime at tn plus 1 minus f prime at tn divided by delta t. So again, for this derivative I'm using this equation, and for this one again I'm using the same equation. So that will give me f t at n plus 2 minus 2 times f t n plus 1 plus f t n divided by the square root of delta t. Okay, so what we see here is, in order to evaluate the second derivative of this function, we need its value 2 time steps away from the current time step. So the first derivative uses the 1 time step, the value 1 time step away from the current step. So that's why we call it a forward difference. Now there's another approach. We call it central difference. So let me draw the same figure. That's t, that's f of t. So let's say that's the variation of f of t. Now here, this is the current time step, Tn. So we will be using the values of a previous time step, Tn minus 1, and another time step, next time step, that will be Tn plus 1. So this is delta t and delta t. And the value of the function, this is f at Tn minus 1. This one is f at Tn. This one is f Tn plus 1. So while taking the derivative, we will be using the time step, the previous time step, and the next time step, and we are approximating the variation by a line. Okay. So that's what we do. Now, in that case, the first derivative will be equal to df Tn by dt is equal to f of Tn plus 1 minus f of Tn minus 1 divided by 2 times delta t. So that's the first derivative. In order to evaluate the second derivative, I will use a different approach. Now first I will use the backward difference. So in other words, I'm using these 2 points to evaluate the second derivative. So f prime Tn minus f prime Tn minus 1 divided by delta t. So this is the backward difference. Okay, and in order to evaluate these 2 derivatives, I will be using the forward difference now, and that's equal to, I have f at Tn plus 1 minus f of Tn minus f of Tn minus f of Tn minus 1 divided by delta t squared. So at this step I used forward difference, and as a result what I get is as follows: f Tn plus 1 minus 2f Tn plus f Tn minus 1 divided by delta t squared. And that's the second equation for the second derivative. Again, we call it the central difference because even in the second derivative we are using the current time step, the previous time step, and the next time step. So here there's only one unknown, is the function's value at tn plus 1, and also here there's another unknown. There's again a single unknown, which is the f of t at n plus 1. So that's why we can use the central difference to numerically evaluate the equation of motion. Before going into that, let's make two definitions regarding the numerical integration methods. So we classify them into, we'll have explicit methods, and the explicit methods is as follows: calculates the state of a system at a later time from the state of a system at the current time. So in the explicit methods, we collect all the information that we have for the current time, and by using that we go to the next time step. Now we have the implicit methods. And we will be discussing what they really mean, what I write here really mean in the upcoming classes. So this calculates the state of a system at a later time by solving an equation involving both the current state and the later state. So in the implicit methods, we gather equations from the current time step and the later time step, combine them and obtain a system of equations and solve the system of equations. In the explicit method, there is no solution of the system of equation. You just determine everything that you know, and from that you jump to the next time step. Now let's take a look at the first numerical algorithm that we will investigate, which is the explicit integration algorithm. And we will be using the central difference method for that. So let's rewrite the equation of motion. This is what we will be trying to solve. So we will be looking at a single degree of freedom system first. We have m times u double dot plus c times u dot plus k times u equal to any excitation force, and in this equation where u double dot is the second time derivative of the displacement and u dot is the first time derivative du over dt. So if I discretize the equation with respect to time domain, so at every time instant, u double dot n represents a time instant, this equation should be satisfied. C times u dot n plus k times un should be equal to p n. Okay. Now for the un and u double dot n and un, I will be using the central difference method. So I have m times un plus 1 minus 2 times un plus un minus 1 divided by delta t squared plus c un plus 1 minus un minus 1 divided by 2 times delta t plus k times un should give me pn. That's the equilibrium condition again at a time instant. Okay, now we discretize it. So instead of having the velocities, we have the displacement for the next time step, displacement of the previous time step. So let's collect everything with respect to the previous time step and the next time step, current time step, and the previous time step all together. So here I have 1 over delta t squared m plus 1 over 2 times delta t c multiplied by u n plus 1. That should be equal to p of n minus k times un plus 2 divided by delta t squared multiplied by m times again un plus 1 over 2 delta t multiplied by c minus 1 over delta t squared multiplied by m and un minus 1. So in order to obtain the displacement for the next time step, we can calculate the following. This is equal to 1 over delta t squared m plus 1 over 2 delta t c inverse multiplied by Pn minus k minus 2 over delta t square m multiplied by un plus 1 over 2 times delta t c minus 1 over delta t square m un minus 1. So what we see here is un plus 1 is unknown, right? It's a state at a later time. And if you look at this one, they are all known. They are all known states. At the current time. And here we are assuming that M and C doesn't change with respect to time. So even if here you have a nonlinear K, you don't have to solve any system of equations, you don't have to iterate, you just use the K at the current time step, multiply it with the known displacement, and when you evaluate all this, you get the displacement at the upcoming time step. So the advantage of this one is it doesn't require a solution of equations. It doesn't require any iterations. So it proceeds in the time domain in a much faster way. The main disadvantage, in order to get a stable, so that you will not get any divergence, very large numbers in the system, you have to keep delta t smaller than a certain value. So this is the main disadvantage of the explicit methods, but on the other hand, the advantage is, again, everything is known, K is known. You don't have to solve any system of equation. You can proceed with just, for the multi-degree of freedom system, with just matrix vector operations. So let's write this as a node. So the central difference algorithm does not require the solution of system of equations. Okay, and uses the known state at the current time step, thus it doesn't require equilibrium iterations. When K is not linear. We will come to that when we discuss the multi-degree solution of the multi-degree of freedom system. That's the main advantage of the explicit algorithms. Now, the main issue with the central difference method is you need un minus 1. So when you start the solution, what is un minus 1 is a critical question. So there are some recommendations for that, but the main disadvantage of this un minus of the central difference is the requirement of the displacement at the time step that you have no idea what's going on. If you want to start with some initial conditions, what is the values of these initial conditions at the previous time step? So these are the main disadvantage of the central different method. If you start from rest, no problem, you can just assume that un minus 1 is also equal to 0. But what will happen if you start with some certain initial displacement and velocity? What's the value of this one? So that's why you don't see much the usage of central difference in the today's commercial softwares. That's that's one of the reasons. And we have the Numerical methods of family of integration algorithms, which is very frequently utilized in many softwares. And our next step is take a look at the Numerical family of integration methods.